What if I told you that something considered waste on livestock farms could be transformed into enough energy to heat thousands of homes? It may sound hard to believe, but that's exactly what's happening in Denmark, home to one of the world's largest biogas plants. Using gigantic artificial stomachs filled with trillions of microorganisms, organic waste is converted into renewable gas that can be fed directly into the national energy grid. So how does this remarkable process work? Let's find out with Mandarin Tech. Energy Korskro is part of Denmark's ambitious strategy to turn waste into energy. Instead of allowing millions of tons of livestock manure and organic byproducts to become an environmental burden, this Nordic nation has built massive biogas facilities that convert them into renewable gas capable of being injected directly into the national energy network. Located in western Denmark, Korskro is one of the largest biogas plants in the world. Each year, the facility processes more than 1 million tons of biomass, producing tens of millions of cubic meters of biomethane. At the heart of the plant are 7 gigantic anaerobic digesters, each holding nearly 10,000 cubic meters of material. Operating around the clock, the entire system transforms enormous volumes of agricultural waste into a valuable source of renewable energy. To produce tens of millions of cubic meters of biomethane every year, Energy Korskro must first solve a challenge that sounds simple but is enormous in scale: how to transform more than 1 million tons of organic waste into fuel. Every day, waste from dairy farms, pig farms, food processing facilities, and many other organic sources arrives at the plant's central reception area. Over the course of a year, the total volume is equivalent to tens of thousands of heavy-duty truckloads. After being weighed, inspected, and cleared of contaminants, the material is shredded, mixed, and pumped into the massive digestion tanks located at the heart of the facility. Inside 7 anaerobic digesters, each with a capacity of nearly 10,000 cubic meters, the organic mixture is continuously stirred and maintained at a temperature of approximately 38 to 40 degrees Celsius. In many ways, each digester functions like a gigantic artificial stomach, operating at full capacity within an industrial complex, where trillions of microorganisms work around the clock. In this completely oxygen-free environment, bacteria begin breaking down the organic material and releasing biogas. The process does not take place over a few hours but continues for several weeks. Every remaining unit of energy within the waste is extracted as efficiently as possible, producing a gas mixture containing methane, carbon dioxide, and small amounts of other impurities. However, this gas is not sent directly into the gas network. Instead, it is transferred to a gas upgrading facility where carbon dioxide, water vapor, sulfur compounds, and other unwanted substances are removed through a series of treatment processes. After purification, what remains is high-quality biomethane with a methane concentration that can exceed 97%. From a practical standpoint, this renewable fuel is nearly indistinguishable from natural gas extracted from underground reservoirs. The biomethane is then compressed and injected directly into Denmark's national gas grid. As a result, energy that once existed in livestock manure, agricultural residues, and food waste can now be used to heat homes, power businesses, and support a wide range of activities across the country. But have you ever wondered what happens to these giant artificial stomachs after years of continuous operation? Although most of the organic material is broken down by microorganisms and converted into biomethane, not everything that enters the digester simply disappears. Over time, sand, gravel, plant fibers, contaminants, and other hard-to-digest materials gradually settle at the bottom of the tanks. After years of operation, this layer of sediment can become tens of centimeters thick, reducing the effective volume of the digester and lowering gas production efficiency. That is why biogas facilities must periodically carry out one of the most demanding maintenance operations in the entire plant: digester cleaning. Before any equipment can be brought inside, the tank must be isolated from the rest of the system and thoroughly inspected. Technicians measure methane, hydrogen sulfide, and oxygen levels to ensure the working environment is free from explosion hazards and dangerous gases. Once the digester has been declared safe, specialized mixing vehicles equipped with hydraulic booms stretching dozens of meters are positioned around the tank. Powerful agitators mounted at the end of these booms begin breaking apart sludge deposits that have accumulated over many years, mixing them back into the remaining liquid inside the vessel. When the material reaches a suitable consistency, maintenance hatches near the base of the digester are opened, and large-diameter industrial hoses are connected to heavy-duty vacuum trucks. Using extremely powerful suction, tens or even hundreds of cubic meters of settled sludge are extracted from the tank. The operation resembles a gigantic vacuum cleaner cleaning out an industrial stomach capable of holding thousands of cubic meters of material. The extracted sludge is then transferred to specialized storage tanks for further treatment or, depending on its composition, eventual reuse in agriculture. However, the job is still not finished. Even after the vacuum system removes most of the liquid sludge and loose sediment, a dense layer of material often remains at the bottom of the tank. This residue typically consists of sand, gravel, plant fibers, and other debris that has accumulated throughout years of operation. Once sludge levels have been reduced to a safe level, technicians bring compact skid loaders and specialized mini loaders into the digester. Inside a structure that normally remains filled with digestate, these machines scrape, gather, and push the remaining deposits into concentrated piles. The material is then loaded into containers or moved to centralized extraction points for removal. Only after the final layers of accumulated sediment have been cleared away does the concrete floor of the digester gradually reappear, often for the first time in many years. At that point, the massive artificial stomach is ready to be returned to service and begin another cycle of converting waste into renewable energy. After understanding how these massive digesters operate and how they are cleaned, another question emerges. How do engineers build an artificial stomach capable of holding nearly 10,000 cubic meters of waste, withstanding continuous pressure, and operating reliably for decades? The answer begins with the foundation, the structure responsible for supporting everything above it. Every megastructure begins by conquering the ground beneath it. To create space for 7 gigantic digesters, engineers first had to excavate a site covering an area comparable to several football fields. Tens of thousands of cubic meters of soil and rock were removed by fleets of heavy excavators and haul trucks. Viewed from above, these enormous machines appear as little more than tiny dots, working relentlessly to carve deep into the earth. The goal is not simply to create a hole, but to reach stable geological layers capable of supporting the immense loads that will eventually rest above. Once completed, each digester and its contents will weigh tens of thousands of tons, making a strong and stable foundation essential to prevent settlement, deformation, or structural damage over the decades of operation that lie ahead. Once the foundation platform is ready, construction of the tank base begins. This is far more than a simple concrete pour. The base must withstand the entire pressure of nearly 10,000 cubic meters of liquid above it. Hundreds of tons of reinforcing steel are arranged in a dense pattern, resembling a giant spider web. Soon after, fleets of concrete mixer trucks continuously deliver concrete into the excavation. The concrete must be poured in a continuous pour without interruption to prevent the formation of cold joints, potential weak points through which liquid could eventually seep. Once cured, the concrete forms a massive monolithic reinforced concrete foundation, as solid and durable as an underground fortress. From this massive foundation, the walls of the artificial stomach begin to rise. Rather than square or rectangular structures, all digesters are built as circular tanks. From an engineering standpoint, a circular shape is the most efficient way to evenly distribute the enormous pressure exerted by liquid slurry and biogas from within. To build these walls, engineers use massive slip-form systems or assemble precast concrete panels with millimeter-level precision. The joints are then sealed with highly flexible materials to ensure the structure is completely gas-tight. Any leakage of methane or hydrogen sulfide could create serious safety risks. As a result, These walls serve not only as the vessel where digestion takes place, but also as a protective barrier for the entire facility. Finally, to seal the system, engineers do not use concrete. Instead, the top of the digester is fitted with a double-membrane biogas dome. The inner membrane is made from highly durable synthetic materials that can withstand exposure to acids and biogas, while the outer membrane protects the structure from storms and the harsh Nordic climate. One of the most interesting features of this design is its flexibility. As trillions of microorganisms below produce biogas, the membrane gradually expands, swelling like a giant balloon. When the gas is extracted for upgrading, the dome slowly contracts again. This continuous cycle of expansion and contraction gives the entire facility the appearance of a living organism, constantly breathing as it produces renewable energy. Those giant concrete stomachs, no matter how impressive, would be nothing more than lifeless structures without the infrastructure that connects them. To transform them into a functioning system, engineers must build a complex industrial network capable of handling everything from receiving waste to delivering purified gas. If the digesters are the stomachs, then the pipeline network is the circulatory system of the entire facility. Tens of kilometers of corrosion-resistant steel pipes and durable-gauge DDPP pipelines are installed throughout the plant. Constructing this network requires exceptional precision. Digestate is highly viscous and can be chemically aggressive, so the pipelines must withstand both the pressure generated by powerful pumping systems and the demanding operating environment. They are also insulated to keep the material warm as it moves through the facility during the harsh Nordic winter. Viewed from above, the pipeline network forms a web of intersecting lines stretching across the complex, linking every section of the plant into a single integrated system. To feed more than 3,000 of waste into the system each day, engineers built a massive receiving hall with large underground concrete reception pits. One of the biggest challenges is odor control. The facility is designed as a sealed structure equipped with powerful negative pressure ventilation systems that continuously draw air inward, preventing odors from escaping. Here, waste is unloaded, processed, and begins its journey into the plant's giant artificial stomachs. After weeks of digestion, the biogas produced is still a raw gas mixture containing methane, carbon dioxide, and trace impurities. To turn it into pipeline-quality fuel, engineers build a gas upgrading unit. This facility consists of tall processing towers where carbon dioxide, water vapor, and other unwanted compounds are removed through specialized filtration and treatment systems. Acting like the plant's lungs, the upgrading system purifies the gas until the methane concentration reaches about 97%, making it comparable to conventional natural gas. This is the final step that completes the entire system. After leaving the upgrading facility, the purified biomethane is sent to a compressor station, where its pressure is increased before being injected into Denmark's national gas network. What began as livestock manure and organic waste is transformed into renewable energy that can be delivered across the country, helping heat homes and power businesses throughout the year. Korskro is far more than a biogas plant. It is part of Denmark's strategy to strengthen energy independence and reduce reliance on fossil fuels. First, energy security. Because biomethane has properties similar to natural gas, it can be injected directly into the existing gas network. This allows Denmark to increase its supply of renewable energy without building an entirely new distribution system. Second, emissions reduction. Instead of allowing livestock manure and organic waste to decompose naturally and release methane into the atmosphere, biogas plants capture that energy and convert it into a useful fuel. Even the carbon dioxide removed during gas upgrading can be recovered and reused by industry. At the same time, the remaining digestate can be returned to farmland as fertilizer, creating a cycle in which waste becomes energy, nutrients, and industrial resources. For Denmark, biogas is not simply a source of renewable fuel, it is a key component of a more resilient and sustainable energy system. Turning waste into a source of energy, Energy Korskro is more than just a biogas plant. It is a remarkable example of modern engineering. By harnessing natural biological processes, Denmark has transformed agricultural waste into a valuable national resource. What do you think? Could this model help address waste challenges in countries like Vietnam? Share your thoughts in the comments below. Don't forget to like and subscribe to Mandarin Tech for more fascinating engineering mega projects. Thanks for watching, and see you next time.